All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandria, and I'm the Assistant Project Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on exoplanetary analog opportunities. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with the questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Abigail Reimer is a space scientist at the Johns Hopkins University Applied Physics Laboratory. She has held many prestigious positions during her career, including being a member of the Cassini's Plasma Spectrometer team and Magnetosphere team, the co-I of the Plasma Instrument for the Europa Clipper mission to Jupiter, and the PI for a recently submitted Neptune Triton concept study. Abby is the exoplanet science lead for the Interstellar Probe Study at APL. Erin May is a postdoctoral researcher at the Johns Hopkins University Applied Physics Laboratory with a focus on exoplanet characterization. Erin received her PhD from the University of Michigan in 2019. She is an expert on climate modeling and observations of exoplanet atmospheres, specifically interested in overcoming systematics and uncovering underlying trends in the atmospheric properties. Erin has experience with ground and space-based observations, working to measure compositions of exoplanet atmospheres with multiple techniques. Sonny Harmon is a planetary scientist at NASA Ames Research Center. He received his PhD in geosciences and astrobiology from Penn State. Sonny studies the interaction between the solid planet, surface, ocean, and atmospheric chemistry of terrestrial exoplanets around a range of stellar types, as well as intermediate mass planets at higher installations in advance of observational campaigns by the James Webb Space Telescope and eventually LUVOIR and HabEx. And now, Abby, the virtual floor is yours.
All right, thanks so much, James. Good day to you all. My name's Abby Reimer. It's been my great pleasure to be guiding the conversation about what research we might do that will further our understanding of our solar system and by extension, the exoplanets beyond our solar system by using the unique platform of the Interstellar Probe. So if we move to our first slide, James. So this, by way of an introduction, is to the Interstellar Probe concept. The idea is to have a spacecraft that will move as rapidly as is feasible out through our solar system to get to at least 1,000 AU with a working lifetime of about 50 years. It's primarily been envisaged by the Heliophysics division at NASA. It's been led by Ralph McNutt, and there's been numerous versions of this throughout the decades. It's a very exciting mission concept, and I think its time is now. And I think one of the things that will enable such a mission, especially given the time that we're living in now and the amount of understanding that we have of planets in our own solar system and beyond, is to really recognize the opportunities to use this to further not just heliophysics goals, but also the goals of the other divisions at NASA. And so that's exactly what I've been tasked to do. And we're also using the Interstellar Probe concept to explore what we might do to further the visions of astrophysics as well as planetary physics goals with looking for opportunities, for example, to do Kuiper belt flybys, but also what we would do with the almost inevitable Jupiter flyby, a very rapid flyby of Jupiter, such as New Horizons did during its cruise out to Pluto. The next slide, please. So some high-level questions that might be answered with regard to exoplanetary research from the Interstellar Probe platform is, how does our solar system look to our nearest neighbor? What would aliens use to look back at the Earth to understand if there really is intelligent, or to the extent that we understand the word intelligent life existing on this planet? And what insights can we gain to exoplanetary systems by observing our own system out to about 1,000 AU? And that would apply to both the planets and to the host stars of those planets. And what techniques are best suited to make those observations, and how can they be accommodated on the Interstellar Probe? So the next slide. So a crucial part of the investigation at the moment is whether or not the install is, for our purposes, for camera hosting, is whether or not the Interstellar Probe platform will be a spinning or a non-spinning platform. So it's our job, and the team have done a wonderful job constructing the buffet of options that we might choose from as we form this really ambitious mission. And one of them is whether or not the platform is spinning. So we've been investigating different techniques to accommodate cameras that can look back into the solar system, and we would have two different techniques depending on whether the spacecraft was a spinner or a three-axis stabilized mission. So if it's a spinning spacecraft, I rather like the idea of a dedicated rear view camera, something simple with a few color filters that will be sneaking a view over the top of the high gain antenna, looking back at the solar system, and actually would make continuous observations, making movies of the solar system as we move out to 1000 AU. Alternatively, and what would perhaps enable a slightly more sophisticated camera for our exoplanetary solar system rear view camera observations, is if it's three-axis stabilized and we actually have a camera suite which is optimized for both doing a Kuiper close flyby observation, the Jupiter flyby observations, but also we would have, as part of the concept of operations, to move back and stare back at our solar system numerous times during our cruise out to 1000 AU. So next slide, please. So our inspiration for this won't come as any surprises. The pale blue dot image, which was finally made by the Voyager 1 spacecraft after its Neptune flyby. The concepts of this was put forward by Carl Sagan, and it was put forward by other members of the Voyager team numerous times before the picture was taken. The observation that it's risky to turn those relatively fragile optics toward the sun, so you don't want to have any sunlight to damage your camera. And in fact, the image of the Earth, which is just 1 pixel in the Voyager narrow angle camera, is caught within the middle of a sunbeam, the scattered light inside the optics. Just a stunning image. And the scientists at the time did propose to make a movie of the solar system, and that was rejected, partly based on the risk of having the cameras oriented so closely to the sun. So what I really hope is that as we're planning this mission, we weave these sort of these observations in from the very start, both for the scientific advancements that we can make, and it's really crucial. We really don't understand what an exoplanet looks like. You know, we can't say, oh, we can model the Earth and imagine what it looks like to a camera from 1000 AU. We think we can do that, but every time we do anything like that, we think we know what we're going to see, and when we actually go back and look, we are always surprised. So the only way to really understand what a habitable planet looks like from a very, very long way away is to do that experiment. And this is one of the unique opportunities to do it. So it's both for the inspiration of it, but also for the scientific exploration of it. And so with that, I will hand over to Erin May, who will talk to us about the benefits that have already been accrued from looking at the solar system planet in the context of exoplanets, and to tell us a bit more about the opportunities from the Interstellar Probe platform. Thank you.
Okay, thank you very much for that introduction. My name is Erin May. I'm a postdoc at the Johns Hopkins Applied Physics Lab, and I'm excited to talk to you today about my thoughts for how Interstellar Probe can benefit exoplanet observations and how we can keep that synergy between exoplanets and solar system observations going forward. So next slide, please. So I want to start by pointing out these observations of Jupiter taken about 50 years ago. These are reflectance spectra of Jupiter, and they're fairly low resolution, low precision observations. But I like this comparison because this is fairly comparable to where we are with exoplanet observations to date. So keeping in mind that we haven't always had these amazing data sets for the solar system planets is really important when we're trying to build these comparisons between solar system planets and exoplanets. And we're really just following in solar system's footsteps with our understanding of worlds outside of the solar system. Next slide, please. So with that in mind, I want to highlight where we are today with discovery of exoplanets. So I'm showing you here a video of the detection of exoplanets over the past approximately 25 years in terms of their planet mass versus how far they are from their host star and their orbital period. And they're color-coded by the detection technique. And what's really exciting is that we're finding different classes of planets than what we have in our solar system. And even perhaps more exciting for the solar system connection is that we're starting to push the limits of our detection techniques and find solar system analog planets outside of the solar system that can help us understand why the solar system looks how it is, and where we came from, and how environmental conditions help create the planets that we see today. And next slide, please. So here I'm really going to focus on transits and direct imaging as ways that that might come into play for how Interstellar Probe can observe exoplanet and observe the solar system planets as exoplanets. So I think an important question to ask at the beginning is, if we want to explore this connection between solar system planets and exoplanets, is should we pick the best solar system planet for this and plan the mission's flight or direction around it? Or should we just let the mission do what it's going to do with its main objectives and pick a planet based off of what we'll actually be able to observe with where Interstellar Probe is going? So next slide, please. So to answer that question, we really would need to start with how we would observe these planets in a way that gives us the most direct comparison to how we observe exoplanets. Primarily with exoplanets, what we're looking at is the total amount of light from a stellar system, which is a combination of the light from the star and the planet, and looking at how the planet's motion in that system affects the amount of light we're getting from the star. So we observe transits of the exoplanet as it crosses in front of its star. And in that case, the amount of light missing from the system is proportional to how much starlight it's blocking, in addition to absorption through the exoplanet's atmosphere. And this is a wavelength-dependent effect. We also observe eclipses when the planet crosses behind the star. And in that case, what we're measuring is the amount of dayside planet flux that's occulted. This is also a wavelength-dependent effect. And then we can also observe phase curves. As the planet orbits its star, different sides of it or phases of it come into view. And this is telling us something about heat redistribution around the planet. And this also can be a wavelength-dependent effect. Transits are really the primary method that we've used to characterize exoplanets to date. So on the next slide, I want to just kind of describe what that looks like. So I'm showing you a GIF on the left of what transit spectroscopy looks like, and this is looking at the transit in different wavelengths. The planet appears larger at wavelengths where it's absorbing radiation due to molecules in the atmosphere, and smaller at wavelengths where it's mostly optically thin to the stellar light. This allows us to create what's called a transit spectrum, which is a plot showing us how deep the transit looks as a function of wavelength and gives us information about what's in the planet's atmosphere. Because this is really the way that we primarily characterize exoplanets, it's important that we look at Interstellar Probe's capabilities or potential capabilities to do these measurements for exoplanet or for solar system planets. Importantly, transits and eclipses require optimal viewing geometry because the planet needs to cross in front of the star from the line of sight of whatever camera is looking at the system. So in the next slide, what I'm highlighting is based off of a given planet in the solar system's inclination, how far above or below the ecliptic plane it might end up in terms of the solar radius. So if it's more than a solar radius above the ecliptic, if the Interstellar Probe is directly in the ecliptic, you're not going to catch its transit. So you would have to adjust the angle of Interstellar Probe's trajectory so that it could catch a transit of a single planet. Because of the low transit probabilities of all of the planets in the solar system, it means it's unlikely we'd be able to observe more than one planet in transit. Now, if we could catch a planet in transit, we need to look at different numbers for how big signals would be. And the first metric for that is just how deep a transit is. So in the next slide, I'm considering just the gas planets in the solar system. So Jupiter and Saturn have about 1% transit depth, which is very doable with today's camera capabilities. And Neptune and Uranus are about 0.1% transit depth, which is also something that is completely doable with camera capabilities today. However, they have very long orbital periods. So there's only one transit or eclipse we could really catch with Interstellar Probe. And because of these long orbital periods, it really would constrain the direction the Interstellar Probe can leave the solar system in order to catch a single transit at the right time for one of these planets. So trying to observe a transit of these gas planets would be very constrictive on Interstellar Probe's main mission goals. But for the terrestrial planets on the next slide, they have significantly smaller transit depths of order about 100 parts per million. Their short orbital periods mean we could technically catch multiple events, which is much less restrictive on Interstellar Probe's direction of leaving the solar system. No matter where it goes, eventually these planets will make their way around during the lifetime of the mission. However, even if we could measure these transit depths, that transit depth itself is not the main determining factor if we can actually characterize these planets. What we actually want to look at is how much absorption there would be through these planets' atmospheres, especially for these small terrestrial planets which have very thin atmospheres compared to the size of the planets. So next slide, please. So what we consider in exoplanets, and thank you to Kevin Stevenson for doing these calculations, is what's called the transmission signal size, eclipse signal size, and then I also have reflection shown here, scaled by a factor of 1,000. Now for the sun, there's something called solar granulation, which is effectively variations in the amount of light that we receive from the sun due to convective cells at the photosphere. And this is at about a level of 2 parts per million. So we would need a camera, or we need to observe a planet that has a signal at least a couple times larger than 2 parts per million in order for us to be astrophysically able to resolve it from the host star's variations. So with that in mind, Mercury, Earth, Mars, probably Uranus and Neptune are not good candidates for transit or eclipse observations. However, there's also the consideration of instrumental effects. So next slide, please. The most precise telescope that we have to date, this isn't considering any future missions, is James Webb, which will launch later this year. And we expect there to be a noise floor of about 10 parts per million there, which means anything below a signal of 10 parts per million, we can't reach no matter how many transits we stack. So while Venus, Jupiter, and Saturn are technically astrophysically observable, really based off of cameras, high precision cameras today, Saturn is really our best target. So next slide, please. So with that in mind, well, technically a mission of Venus, a mission or a transit of Jupiter, or a transit of Saturn are something we could observe. The transit of Saturn is really the only one that has a signal size large enough. In addition to that, we don't really have good exoplanet analogs for Jupiter or Saturn yet because they're very cold and far from their host stars. So the couple of them that we do have require a lot of transits to build up the signal that we need to measure their atmospheres. And it's not really something that we expect to be able to do in the next decade or so with James Webb. So with that in mind, it leaves us with Venus is probably our closest exoplanet analog, but it's not something we can do in transit or eclipse because of its small signal size, requiring a precision around the solar granulation level. So that brings us to the question, could we directly image the planets in the solar system? So in the next slide, I'm showing you some examples of direct imaging of exoplanet systems. And these are really exciting images because we're directly resolving the planet from its host star by blocking out the stellar light in the center. And these are primarily young, warm planets. But one of the exciting things about direct imaging is it might allow us to study multiple solar system planets without relying on transit geometry. And while we don't have a lot of direct imaging observations of the solar system type planets to date, it's something that we expect to be able to discover in coming years while we wait for Interstellar Probe to launch. So this idea of what would aliens be able to see if they looked at the solar system, on the next slide, I'm showing an example of what the solar system would look like at 13 parsecs, which is approximately 13 million astronomical units away. If there's a 12-meter telescope looking back at the solar system with a coronagraph at the center, which is blocking out the solar light. In this situation, Mercury is within that inner working angle, but Venus and Earth and Jupiter are resolvable, and you can measure the amount of light from each planet and build up spectra. So if we were able to do something comparable with Interstellar Probe, we could look at how these planets compare to each other and compare to exoplanets as we begin to discover exoplanets that we can directly image that are similar to these in the system. So we can do a little bit of a thought experiment with what would Interstellar Probe be able to observe in direct imaging. So in the next slide, I'm showing you the maximum angular distance from the sun any given planet could be if Interstellar Probe was 500 AU away. So they range from about 2.5 arc minutes to 200 arc minutes, or about 5 degrees or so. And they're all technically separable from the sun then at some point during their orbit, if we were using a chronographic technique. But to observe all of the planets, the field of view would need to be about 10 degrees with the central chronograph, which is quite large for typical direct imaging missions. So it would make observing more than one planet at the same time difficult if we went with standard chronographic techniques. And in addition, you also have to consider the relative flux difference between planets and the sun. So the next slide, I'm showing calculations of contrast to the host star for various planets based off of standard chronographic techniques in order to require a contrast ratio of about 10 to the minus 10 to detect solar system planets, which means being able to image things that are quite different in brightness in the same field of view. And this is actually beyond the limit of current chronographic techniques. So that tells us that imaging the solar system planets with Interstellar Probe requires removing the sun from the field of view. And now we're getting away from direct exoplanet observation techniques, but it's still a method that would allow us to measure things about the emission of the atmosphere and compare them to what we learn about emission from exoplanet atmospheres. So if we just want to look at the total amount of emitted flux from a planet, irrespective of the contrast to the host star, we can plot up the amount of emitted flux times the planet's area. So in the next slide, I'm showing that in arbitrary units for all the planets in the solar system. And I've highlighted a few chronographic bands that James Webb will observe in the coming years. And there are, of course, future generation missions in development, but I haven't included them there because they haven't been selected yet. But what's important here is that Venus is still the largest signal in that case. It's so warm that its black body emission just dominates over Jupiter, even though Jupiter is quite a bit larger. So this brings us back around to the idea of planning the mission as backwards facing camera around being able to measure emission from Venus. In particular, on the next slide, I'm showing you how Venus actually compares to some known exoplanets. The TRAPPIST-1 system is a nearby system of 7 approximately Earth-sized planets, all kind of scaled to where the terrestrial planets are in our solar system. This is a very exciting system that astronomers are really planning to use all the available techniques and telescopes to characterize over the coming years. And Venus is fairly similar in size and the amount of light it gets from its host star to TRAPPIST-C and TRAPPIST-D. And theoretical models predict that these atmospheres might be carbon CO2 dominated like Venus. They might have gone through runaway greenhouse phases during their evolution. So if we can look at Venus as we would at an exoplanet with Interstellar Probe, it's going to provide insights into CO2 dominated atmospheres that will allow us to understand these TRAPPIST planets better, particularly when we have these closer observations of Venus we can tie our exoplanet analog observations to. Next slide, please. So in particular, what's special about Venus is the strength of the CO2 features in the emission spectrum. So on the left, I'm showing emission spectra for Venus, Mars, and Earth, and you can see that the size of that CO2 feature really varies depending on the atmospheric composition. Emission spectra observed with James Webb now in the direct imaging sense are just going to be a few bands, but with James Webb we'll be observing eclipses of these planets, which is essentially going to give us a way to measure the sizes of these features for planets outside the solar system. So it's a really exciting possibility to understand what these TRAPPIST-1 planets are like and how their evolution and did they go through runaway greenhouse effects like Venus did in its history. So my final slide, I'm kind of leaving you with my thoughts that if we could only observe one exoplanet with Interstellar Probe and we needed to optimize the camera to do that, I really think Venus is our best bet because it's the closest to a true exoplanet analog to date with a large signal. And this is, of course, just my opinion, so feel free to disagree with me, but I'll leave you with that, and thank you. I'll take questions at the end.
Thank you very much, Erin. And now for Sunny's presentation.
Thank you very much. I would like to expand a little bit on some of Aaron's points, which I think are very good in this particular concept. And I want to sort of cast it a little further in the future when we start talking about things like the larger space telescopes that we're currently drawing out to see whether they make sense conceptually. And so next slide, please. I want to start with the big picture and work our way down. And as Abby showed earlier, this is, of course, the pale blue dot superimposed over the wide field camera that Voyager 1 took back when it was looking back at the solar system and painting the family portrait of all the planets. And as you can see, there's a lot of things in here that aren't necessarily great observing. And as Aaron mentioned, there's the problem with seeing starlight in your telescope as opposed to seeing the planet's light. And the practical effect here is that you're not necessarily getting the signal that you want from the planet. You can also see that there's lots of artifacting and potentially some dust or some other observable phenomena that are happening that are obscuring your signal that you would otherwise like to see. But this is a really good practical experiment in actually observing at sort of moderately large separations from the object of interest. Next slide, please. And in combination with this desire to find life elsewhere, right? So the pale blue dot image tells us that the Earth is part of a vast emptiness of space, but also in combination with other data sets like the Galileo flyby, we can see that the Earth has clear signs of life on it. So the oxygen band at 0.76 microns, abundant water vapor features through its spectra. These all are really good indicators for the fact that not only is the image of the pale blue dot captivating, but it is compelling from a scientific standpoint and provides one of our real only milestones for what life would look like around another star. Next slide, please. So because of the fact that Earth is our only example, it has become a common touch point for a number of different observational techniques and for modeling techniques. And so you can see here two different studies that have attempted to leverage extant data sets to validate models and to expand on what we think the Earth is going to look like from different viewing geometries from sort of those interstellar distances. And so on the left, you have some data from the Epoxy mission, which was a reuse of the Deep Impact mission. And you can see that the Earth data that you're getting from Epoxy is a really fantastic tool for validating the practical appearance of the planet between two different versions of the model. And then on the right, you can see that again, that refinement of our techniques for simulating what these planets are going to look like includes the addition of data from L-Cross, which fantastically highlights the fact that you get information other than just the chemical components of the atmosphere or the spectroscopic components in that respect, but you also get things like, for example, the influence of surface oceans and glint off of those oceans on your spectroscopic observations. And all of these together really paint a fantastic picture of what exactly it is that we could see when we go look at exoplanets. Next slide, please. Now, sort of backing up to think about what are the sort of the practical hurdles here. Obviously, Aaron showed some fantastic images from, I think, another component of the haystack study. But you can see here that looking at the solar system, you're not just going to see the planets. Obviously, you've got the bright central star, but there are other confounding factors like the presence of dust. This is the zodiacal dust rings that we have in our own solar system, and the fact that you have other bright objects like Jupiter and Venus that, as Aaron mentioned again, are substantially brighter than the objects that may be of more interest for particular avenues of research, like thinking about life on other worlds. And so I think that this really highlights the fact that you're in this really interesting middle space with Interstellar Probe, where you have ground truth because you start the mission close to the Earth. You can make really strong spectroscopic observations, potentially with an onboard spectrograph or camera, multicolor camera. And then you get the confounding factors that slowly accrue as the separations between the objects increases. And this is true not just for the Earth, right? The other planets that we see here have their own unique spectroscopic signals that tell us really interesting things about those planets. Next slide, please. Now, again, this is, again, some of Aki Roberge's work, thinking about the spectroscopic observations of these planets. And you can see that these are synthetic spectra of all the planets, excluding Mercury, as seen from quadrature at 10 parsecs. So fairly large separations. And this is with a perfect telescope. So you're not seeing any sort of contamination from the star that they're orbiting, for example. But all of this information tells you a lot of critical details about the fact that some of these planets have clouds and or hazes. Some of them have high surface temperatures. As Aaron mentioned, Venus has a very high surface temperature, and so it dominates in the infrared in terms of its spectral flux density as compared to the other planets. And it tells you about composition, like I highlighted for Earth. The fact that it has water and oxygen in its atmosphere really does have a distinctive effect on its spectra. And while you can see all this in gory detail because of the synthetic nature of these spectra, even low spectral resolution observations can still give you useful information. For example, you can notice that the near UV and the short wavelength observations have very distinct slopes. So the fact that they have different Rayleigh scattering tells you something about the composition of the atmosphere and what it does to the spectra. And the differences between, for example, the visible and the near IR give you, again, that factor of surface temperature or lower atmospheric temperature and how that transmits through the atmosphere. And all of those are super useful in validating our tools for making these types of observations. But again, I would highlight that the higher spectral resolution, say 20 or 100 points through the visible and near IR, gives you really critical information, not just about those sort of first order effects, like the fact that it has an atmosphere, but it also gives you information about things like composition and structure, like clouds and hazes. So I would argue here that even if you're looking at these planets with a smaller instrument, that including that spectral component is a really critical one to getting a novel data set from Interstellar Probe. Next slide, please. Now we can start to paint a picture of what Interstellar Probe looks like in the course of its journey. So here's one notional course where we're looking at an Earth launch in 2030 that goes by Jupiter for a gravity assist and then ultimately flies by Quaoar. And I've done some sort of back of the envelope calculations here to try to figure out what that looks like for myself. And over the course of that sort of 5-year mission, you can see that we travel a significant portion of the solar system. And you can see that the arcs here are really the amount of travel that the planets are experiencing through some part of that trajectory. So you get a large variation in phase angles over that whole trip, just for that short 5-year or 6-year first window. Next slide, please. And we can even go so far as to make videos. And this is just the first 15-ish years of what a Earth, Jupiter, Neptune, Eris mission would look like. And you can see here it goes through the goldenrod point labeled N, which is Neptune, right at when it should, which is nice. And so again, you can see that over the course of this, even the first 15 years of a notional 50-year mission lifetime, you're getting substantial variations in where the planets are with respect to the star. And that can be really critical for figuring out what the phase angle variability of those objects are. And if we get spectral information on top of that, that is a really unique data set that is largely unparalleled, except in aggregate from a number of other spacecraft and observations that we've used to sort of validate stuff. Next slide, please. And of course, the Earth, Jupiter, Neptune, Eris is just one of the potential mission profiles. So there's a number of other potential avenues here for getting the spacecraft out into interstellar space, which is the primary objective, obviously. But because ISP has such a long mission lifetime, and because ISP is traveling across that whole expanse, it has a fantastic view of most of the objects in the solar system. So not just the inner solar planets, not just the outer solar system planets, but just the whole gamut, and across multiple orbits of those planets across those tens of years, right? And so even with a small diameter telescope, the objects that you're trying to look at, the planets in the solar system, are physically separable from the sun for most of that trip. And as Aaron pointed out, just because they are theoretically separable doesn't mean that they are practically separable. There are additional impacts that have to be overcome, likely with engineering and detailed analyses of how you make those observations. But as we saw from pale blue dot, you don't have to have a coronagraph to do those types of rearward facing observations. You just have to be careful not to look at the sun. And yes, there's much more to it than that. I'm dramatically simplifying the fact, but an off-axis camera with a wide field of view on a rotating spacecraft, which is something that the heliophysics community is, I think, partly in favor of, gives you a really unique observational hurdle that I think directly parallels what we might expect to see for exoplanetary systems, where you look in direct observing whether or not you're going to see the planets in that system, and because you can't separate them optically from one another because you're just looking with a big telescope from very far away, you get the aggregate signals from those planets in that viewing window. And if we do the same thing here, it's a really excellent testbed for figuring out how you disentangle those signals. So next slide, please. So I think, as I've highlighted, and I think as Aaron's mentioned, there's lots of hurdles, obviously, to making these look-back observations, but they provide normally inaccessible viewing geometries and conditions, and getting that high phase angle observations of the giant planets, which we currently don't have except for very piecemeal from other platforms, gets you to a unique data set that is unparalleled in the planetary science and exoplanet community. And because of that unparalleled duration of the mission concept at present, it gives you a really fantastic view at sort of the variability and the potential for what these planets are going to look like over time. And because you're getting those unique observational modes, and because you're getting that new data, you're providing a really unique aggregate data set from a single observational platform that I think is really worth pursuing for that particular aspect of it. And because, again, of the unique nature of the ISP mission, it's a really great proving ground for a lot of next generation observational techniques that we're going to need to start thinking about. And obviously, there are going to be unique challenges for this, but I think that adequate planning and engineering can help address some of those. And that's all I have for you. Thank you.
Thank you very much, Sunny, and thank you to all of our panelists. We're now going to go to our question and answer session, so please feel free to post questions in the Q&A feature of Zoom. And so the first question from Miho Hanvir is to Aaron May. On slide 17, you talk about how solar granulation has to be taken into account. But what about solar cycle variations, and as such, star cycle variations on the light emitted? Should this also be taken into account?
Yeah, so if you're trying to do relative measurements of a planet compared to its star, knowing the absolute amount of light from the star is incredibly important. And with exoplanet observations, we're typically able to do photometric monitoring of the stars outside of those events, so you can track variations in the amount of starlight and correct for that due to their own stellar cycles. With the sun, we obviously have tons of instruments that are observing the sun, and we would be able to make those corrections if it became necessary to do relative measurements compared to the sun. As I pointed out, I don't think transits are feasible with Interstellar Probe, and we want to separate the sun from the field of view of the planets with direct imaging. So it is unlikely to be something that would need to be considered. But yeah, that's a great question.
Thank you, Aaron. And our next question is from Marav Ofer to Sunny. What is the status of studying the effects of GCRs on atmospheres? I know we have discussed it before, but would like to hear your thoughts.
I think it's still a developing field. I know that there's been a few more works that have come out, I think, of some of the European groups about thinking about high energy and particle radiation on planets. There's also been some work from Matt Tilley and from a few other folks, I can't remember off the top of my head, who have looked at it, but I think it's still a developing field. I think until we get observational constraints on what that does to planetary atmospheres, it's going to be a whose model is whose sort of approach to things. But yeah, I think it's still a developing field and it has some really interesting implications for habitability.
Thank you very much, Sunny. And our next question is from Stephen Dare. We discussed a concept in November on deploying a series of CubeSats for solar system and exoplanet observations to compensate for the rotation of the probe. What would be a recommendable size for a panchromatic and LiDAR aperture? I'm going to give this question to Abby.
I don't know the answer to the last part of the question, but the first part of the question, yeah, that was a very interesting concept suggested, I think, first by Alan Stern. We did, and I took it over to the exoplanet working group, which we discussed and are including in our, at least the memo version of our report now. I'll remind you that the leading tagline of the mission is the pragmatic interstellar probe. We are really looking for technologies that currently exist that can be implemented in, albeit imaginative ways. And I think that the docking and the undocking of those CubeSats, while really making sure that we pull on every thread, because if it's going to give us a scientific advantage, we want to make sure it's properly documented, but it hasn't been something that moved forward in our planning of the options for these for the exoplanet camera. So on that, I'll remind you that from the start, we even talked about making direct observations of exoplanets from our platform. We look back at including the coronagraph images, and then now looking at opportunities from a spinning and a non-spinning platform, but we haven't included observations from something that separates from the spacecraft.
Thanks, Abby. And our next question is from Ralph McNutt. For one version of the Interstellar Probe for heliophysics observations, a spin rate of 1 to 5 RPM for the spacecraft has been envisioned. Is this too fast for a look-back camera to work? I would want to have to slow down the rate to enable observations. So I can give this to Aaron and then to Sunny, if you'd both like to comment.
So I am by far not an expert on spacecraft design, but one of the things that we really are concerned about with exoplanet observations is precision and trying to keep observations on the same pixel or as close to that as possible. Now, when a planet is moving, like with direct imaging, that's not necessarily possible, but the spin rate could essentially make it hard to make observations at a precision level that would be that would allow us to make these comparisons to exoplanet observations.
And I would second that the fact that you're smearing it potentially over several pixels is potentially problematic for traditional techniques. But I think the fact that this is a fairly non-traditional platform for doing these types of observations means that we have to sort of pivot away from thinking about just the way we've done it before. And there have been a number of really interesting techniques that I can't recall the specific nomenclature for off the top of my head, but basically smearing an object over several pixels gives you, I think, another way of capturing that same amount of information. And if you're thinking about this in terms of just integrating signals and making a direct analog to direct imaging with exoplanet systems, just having it all sort of mashed together in a single data point is difficult in its own way, but I think it gets around some of those technical challenges that you mentioned, Ralph.
And I'll add, we did have a presentation to the working group from Candy Hansen, who's the director of the JunoCam, which is the community instrument, if you like. It's not part of the official science payload of the Juno mission at Jupiter, which is spins at, I think it's faster than 1 RPM. Which makes absolutely fabulous measurements, albeit very, very close up of Jupiter's atmosphere. So we are really keen, because one of the things that's relatively cheap is if we don't develop the technology, but we develop the data processing necessary to do what Sunny's just been talking about, is something that we're making sure we keep a close eye on as part of this opportunity.
Thank you all very much. And the next question from Chao Chin Yang. Is 1000 AU the current technology limit at which we can still communicate with the probe? And I'm going to pass this question to the project scientist, Pontus Brandt.
Yeah, so a quick answer is probably not. The way we're thinking about 1000 AU here, what really limits that is power. It's the RTG on board to be able to drive the radio antennas, and this is X-band antennas that we're considering, 5 meter AGA. While at the same time, you should be able to have at least several instruments on. So probably one could push that further than 1000 AU, but that's of course an engineering question.
Thank you very much, Pontus. And the next question is from Elliot Clevo. To any of the presenters, what is the technological bottleneck in imaging techniques that could be addressed in the coming decade? Could the imaging limits be simply addressed by launching a more massive probe with the larger optics, or something more fundamental, lacking? And I'll give this to both Aaron and Sunny, and then Abby as well, if you'd like to comment.
I can start. I think a lot of the bottlenecks are our limitations really are astrophysical in nature. You know, you can create a better and better camera, but at some point you reach some astrophysical limit of just noise from the objects themselves, or background, like stray sunlight. Yeah, I mean, we were already building cameras that have high precision. We're just limited by the objects themselves.
I have nothing to add. Aaron perfectly captured it. Yes, some of these are astrophysical and practical and just optical limits. And yeah, it would be great if we could launch, like, you know, a 12-meter space telescope into interstellar space, but I think that raises a number of other engineering concerns that we might have.
And it's one of the things that makes the concept of this mission such an enjoyable thing to work on, is that we haven't been given an explicit mass box, but it's also, that means the onus is on us not to say we can put another Hubble Space Telescope on Interstellar Probe. So we have to strike the balance between wanting to launch something that was really state of the art versus putting something on there that could be realistically accommodated by such a mission.
Thank you all very much. And the next question is from Paul E. Lane. Is exoplanetary analog opportunities included in the probe's general trajectory planning? And I'll give this question to Abby.
It is not. So there's the idea of the direction that the Interstellar Probe exits the solar system it's so important for the observation of the actual edge of the astrosphere, which emits in these energetic neutral atoms, and they have dedicated cameras on the Interstellar Probe in order to make those measurements. Those measurements have been made previously by the IBEX spacecraft at 1AU at the Earth, and also by Cassini, wonderful, amazing observations that they hadn't anticipated making out to Saturn's orbital distance at 9 AU in the solar system. So it's absolutely vital that the Interstellar Probe is optimized to make those measurements of our astrosphere from the outside looking back in. So we had a lot of very fun conversations about going and doing the Neptune flyby, and also other things that could optimize for exoplanetary type observations. But in the end, the opportunity the need to optimize the observations for that astrophysical observation trumps the solar system one, which is fine, because the real key is the baseline is being far away to look back. It's not necessarily the direction so much. So we're good.
Thank you very much, Abby. And the next question is from Chao Chin Yang. Could you elaborate on the potential of detecting KBOs on the way? And Sunny, would you like to take this question?
I certainly can. I'm gonna channel my inner Kirby here, and I mean, I think that the potential for detecting KBOs is I think, on the edge of the practical, but the potential for characterizing known KBOs, I think, is really excellent, and you can get a really great vantage point because you're flying maybe not by a number of KBOs, but you're flying closer to the KBOs than any other spacecraft that we currently have. So something like doing a follow-up with different types of objects than what New Horizons has seen and will see would be, I think, a really interesting orthogonal observation that would be a compelling additional mission point to hit. So I think it's definitely foremost in what we're thinking about in terms of planetary science, and I think it's going to really develop into a compelling story about KBOs.
Yeah,
Thank you very much.
I can jump quickly in here for Sonny as well. So Sonny is right. So one of the things that we are currently planning on as well are these high solar angle light curves to look at KBOs out there for over a pretty large distance. But that will tell you something about their rotational dynamics as well at different angles than we can observe from Earth. So very simple.
Thank you. And the next question is from Stephen Dare. Thank you for the answer, Abigail. Would having the CubeSats deploy and remain at various planetary Lagrangian points be an efficient and effective way to overcome the issues of docking/undocking for a long-term imaging solutions. So I'm going to pass this to Abby, and then Pontus, if you'd like to weigh in, please do so.
So I'll start from the visionary point of view, since Pontus can't reach to gag me, and then I'll let him tell you whether or not it's part of a plausible pragmatic solution, because I love that idea. And numerous missions have looked at missions of opportunity. For example, I believe Europa Clipper did in the early days. We had a mission of opportunity. Call went out for people to suggest CubeSats that could ride along with it. And I do wonder that any mission that's going to the outer solar system, it's beholden on us to give the most return to the taxpayer by looking at other things that we could do along the way. And that's a great idea. Dropping some CubeSats off, perhaps they could use the Interstellar Probe as a mothership to telemeter data back for on the order of minutes, hours, days, to gather some information along the way. It's difficult to imagine how they would sit there and actually telemeter data on their own once the mothership has passed by, but perhaps the opportunity to drop CubeSats at Jupiter and use real estate that's already there to telemeter the data back from that orbit and leave cameras there. We haven't thought about that, and if that's, maybe we could add that to the buffet, Pontus.
To the buffet, certainly. So as always, I think when, so this question has sort of come up before in various forms in terms of dropping stuff off along the way. I think once you start looking at the numbers, the engineering, and especially in terms of the mass that it requires, but also the communication and power systems that you would need on the CubeSats, and if you would like to go into an orbit around a Lagrangian point or be sort of semi-stationary there, you would also need to consider propulsion systems, right? Do remember that the plan is to launch on the pretty much the largest launch vehicle we have, which is currently the SLS Block 2. And our trip to Jupiter will take about 7 months. After Jupiter gravity assist, we will be slingshotting out at about 36 kilometers per second. So if we put those numbers together, it is not going to be simple. But it's definitely something that has been coming up before, and we can keep thinking about it.
Thank you. And for our last question, again from Stephen Dare, reflecting on Kirby's comments in December, what centaurs of interest would be available for observations and experimentation? Abby, do you know, or would you like to take this one?
I do not know. I believe that from our experience talking about centaurs and KBOs in general, the idea is that irrespective of the direction of exit, we should be able to image at least one centaur and at least one KBO.
Okay, thank you very much, Abby. And that's all the time that we have for today. Thank you very much to our panelists, and thank you for attending today's webinar. Please visit the Interstellar Probe website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv under the community involvement section of the website to make sure that you're getting the latest information on the upcoming webinars and events. Thanks for joining us, and have a wonderful day.
Thanks, everyone. Bye. Yeah.